on through. So if you look at it, it's just a continuum. It's a continuum, it's a build-up. So virtually you see that we've not departed from where we started in terms of thermodynamics at the beginning. You're going to see at the end of today's class, we'll be going back to talking about adiabatic system again. We'll be moving on to talk about the fact that you have a system, so you have a surrounding, there is a boundary. Those are things we talked about at the beginning of the course. So you see that it's a build-up. We're just continuing, from there. Another thing that I want you to take note of is, so that's why you cannot learn in boxes, that even though we've been dealing with this subject in chapters, you see that it's a continuous thread. Another thing I want you to take note of is, at least for the past couple of chapters now, we've been focusing more on how heat is transferred. In the last two classes, in chapter 12, actually the last three classes in chapter 12, in chapter 11, and in chapter 10, you see that we looked at steam as carriers of heat, or we use steam for to mediate work, to get work done. So we've done that, in the past couple of weeks. So today we want to look at another thing, which is called heat effect. Before we move on, and you're going to see from today's topic that there are things that you're familiar with, things you've seen in chemistry over and over, in different ways. You can also see from the topic already, chemical reactions. So I want to start by asking, can someone describe to me what endothermic reaction or process is? Another person to please define what exothermic. So I want someone to describe exothermic, another one to describe endothermic. Exothermic, endothermic. Any takers? Please don't hesitate. You can raise your hand using the reaction thing at the panel, or you can just type it out. Someone who is going to describe to us what an endothermic process or reaction is. And we want someone to describe to us what an endothermic process or reaction is. So endothermic and exothermic. Okay, Juju is saying it gives off, exothermic gives us heat. Lunga is saying endothermic builds up heat. Okay, so we can see Lunga no. Okay, Juju, yes. During endothermic reaction, energy is absorbed. So specifically, that's what Marciani said. I hope I called your name well. If I didn't, forgive me. So it's saying during endothermic reaction, energy is absorbed. So you're right. So we just need to be more specific, reaction energy. So we can say heat. Thank you for that. Maria, in endothermic reaction, heat is absorbed. Yes. Fabi, exothermic reactions involve heat being released during reaction and absorbs it. Good. Yeah. So good. Endothermic processes require an input of energy to proceed and are signified by a positive change in enthalpy. Well done, guys. Luyolo, I want you to, if you take note, I want you all, please, for those who are taking notes, I want you to take note of everything everyone has said. One, you could see definition by talking at release of energy, definition talking about absorption of energy, definition talking about positive or negative enthalpy. So I want to take note of all those. Those are important. The third definition that I see from what you've all stated, which is very important, is that for endothermic, it cannot proceed. And if you remember, when we're looking at the first, second, and third law of thermodynamics, we talked about, I believe it's the third law of thermodynamics, where we talked about, a process cannot proceed without a certain thing being put in place. So yes, so those are the definitions. So well done to everyone that has contributed. I know some are shy to type in something, but for everyone, so please, I want to take note of those three key definitions: the part of heat being released or absorbed, the part of enthalpy change being negative or positive, and thirdly, the part of heat being needed to be added for a process to take place or not. Thank you. So please, let's engage some more. Let's engage some more. So thank you for that. So you've pretty all described this, and let me warn you ahead of time, quite for today's class, we'll be seeing quite a number of definitions. Some of them I'll skip because I believe you can easily look through them. And once I skip, I require you to please go through them towards tomorrow's class when we do calculations, so that whenever we are looking, whenever we have some assumptions during the calculations, they wouldn't be strange to you. You see that the assumptions or the definitions are from today's class. So heat of reaction is the change in enthalpy. So now we are seeing what one of the definitions stated earlier on, the heat of reaction. So it has to do with the enthalpy. So, and it proceeds at constant temperature. And the enthalpy change or heat of reaction, we look at it based on the difference between that of the products and all the reactants. So which is the equation 13.1, which I believe we are all familiar with. And in one of the definitions, it is stated that change in enthalpy, if it's negative, it is exothermic, even though the energy itself, take note, the energy inherent itself, the heat itself is positive. Remember, for it to be, because the temperature is increasing, so the heat itself within the system is positive. So that is why another thing, to cast our mind back to what we saw at the beginning of the year. Remember, we talked about you have a system. So you have a system, and then you have a surrounding for the system. So in an exothermic process, so you have heat within the system, the temperature is increasing, and based on that, there is heat released into the surroundings. So heat is released into the surroundings. So I've got my coffee here. So inside, the temperature is positive, and as I'm holding it, I can feel the warmth, because heat is being released into the atmosphere. So that is exothermic. But in endothermic, oftentimes it requires heat on the inside. So in endothermic reaction process, it takes heat from the surrounding. So it takes heat from the surrounding for it to proceed. So for an ice to melt, for example, it requires heat from the surrounding. So those are the things that I want us to take note here. So please, in case I get to a point, you miss certain things, you want to clarify it, you please never hesitate to raise your hand. And since it's being recorded as well, you can go back, pause, and play. So the standard, so starting the reactions now, I mean the definitions now. So whenever you see standard, as we move on, you're going to see more definitions where it talks about standard. So oftentimes when we define any of these definitions that I'll be looking at, when it is standardized, when it is called standard, remember in the previous slide, we just mentioned heat of reaction, but now we are being more specific, you're saying standard. So whenever you see that word standard, a couple of things that you need to bear in mind. One is that there is a reference point, and the reference point is usually a standard temperature, or what we call standard state. And the standard temperature in this case is usually ambient temperature, which is about 25 degrees centigrade, which is equivalent to 298 Kelvin. So 25 degrees centigrade, which is equivalent to 298 Kelvin. So whenever we talk about standard, we're talking about standard temperature, 25 degrees C or 298 Kelvin. The second thing we are talking about is standard pressure, which is one atmosphere. So please take note of that. So 298 Kelvin, the temperature, and 1 atmosphere for the pressure. So those are the two things I want to take, a couple of things I want to take note of there. So moving on. So let's consider the reaction. And if you look at what we've seen prior to now, we looked at products, reactants. So what this means is that for us to know the heat of reaction of an entire reaction, we need to be able to know the heat for the different components, the heat, and we call it heat of formation. So let me repeat that again. So for us to know the heat of reaction for a process, a process is complete. In the process, you're having transformation from reactants to products. So in order for us to be able to know the heat of the entire process, the heat of reaction of the entire process, we need to know the heat of formation for the individual components in the process, the heat of formation for the reactants, and the heat of formation for the compounds. So take note of that. Another thing I want you to take note of, so how do we get the heat of formation for each reactant? There is a table. I've provided that on Blackboard, part of the materials that I've made available. So for each compound, there is a heat of formation for them, which has been, so we just go to the table and then we look at the heat of formation, and then we, looking at the reactions taking place, we can then add them up. Another thing I want to take note of is this. Whenever we are dealing with the standard, remember, as we mentioned, it should be at 298. So the table that we'll be using measures everything at 298 Kelvin. And then also note that whenever we are dealing with reactions for elements, so this is an element, you can see it's just one. For elements, heat of formation is usually 0. We'll see that better in the calculations tomorrow. But I want you to look at I've solved the calculations already. I posted the PDF. So tomorrow we'll just discuss. So you see that for elements, the heat of formation is usually 0. And then for compounds, we have values for them. Also note that the heat of formation, the heat of reaction for every process is directly proportional to the number of moles of the compounds present. Can I say that again? The heat of reaction for a process is directly proportional to the amount of moles of the compounds present. So that is why you see that in the first reaction, when we just add 1 carbon, half oxygen, and on, the heat of reaction was 110. When everything was directly doubled, you see this times 2, times 2, everything was directly doubled, you see that the heat of reaction 2 has been directly doubled. So take note of that. So I've talked about issue of heat of formation for individual components in a process. So we've mentioned that, and then I've talked about how heat of you pull all of them together for that to, we pull all of them together for us to get heat of reaction. So I've talked about this already from the previous slide, but let's just look at what we have written here. So the change in enthalpy accompanied the formation of 1 mole. So that is why you're going to see that whenever we are doing the estimation, we'll say per mole, per mole. So that is why if you go back to the previous slide, so even if you are dealing with the heat of formation or heat of the process for carbon monoxide, you're going to see that it's still going to be per mole, and it's still going to go back to 110. So it's usually per mole. So for example, heat of formation of carbon monoxide, that is a compound, not an element. So remember we said for element, it's 0. So for a compound, different component elements come together. Different elements come together. So 1 mole of the substance from the constraint element is termed heat of formation. So as I've talked about this, the standard heat of formation of these, and you can see, as I mentioned, this is available in a table, just as we have steam tables for the previous classes. For this particular one, we'll be using what we call standard heat. We'll be using that table, the standard heat table or enthalpy table. So we'll be using that. So see enthalpy table. We are going to also see what we call Gibbs energy table. All right, so moving on, there is a law that underpins what we've been talking about, and this law is called the Hess Law. Hess Law. From that, you can see that's someone's name, Hess Law. So it's a law of constant heat summation. So in essence, this just summarizes everything we've been talking about, that when a process occurs in steps. So in previous slide, I've talked about different elements coming together to form compounds, and the need for us to take note of the heat of formation for different components of the reaction. In this particular case, in the Hess Law, which summarizes the entire thing, the Hess Law is saying that in many cases, reactions take place in steps. So all you need to do now is look for the heat of formation for each step, and then you sum the steps. So let's look at that in the next so let's look at that. So for example, the formation of NO2 takes place in 2 steps. So if you remember from chemistry, so we have in some cases we talk about how in electrochemical process, for example, we'll talk about half reactions. So these are the 2 steps. So if you sum the 2 steps, you have the final reaction there. So in the same way, you sum the 2 steps, so you balance everything out. Half O2, half O2 gives us 1. We also sum their enthalpy changes, their heat of formation. And then what are we going to say about this particular process? Is it exothermic or endothermic? Any taker in the class? So we sum it up, and then from it, is it exothermic or endothermic? And will the process be able to occur spontaneously or not? Any takers? No response. Thank you. Endothermic, it will not occur. Endothermic Luyolo, it will not occur. Yeah. Yeah, Juju, thank you. Yeah, endothermic Manla, thank you. All right, thanks everyone. Good responses from there. You know, oftentimes when you engage like this, it sticks better. So that's why I want this engagement to occur. So thank you. So it's endothermic. It's signified by positive change of enthalpy. Thank you, everyone. All right, so we'll move on. So we've said the net heat evolved or absorbed. So what are we going to say in the case of the previous step? We'll say net heat in the case of what we saw just now. So we are going to look at net heat absorbed. So it's going to be net heat absorbed. So because it's endothermic, so can be calculated. I've talked about this. Can be calculated from a series of reactions from its elements. So let's take note of that. So in one of the definitions you see, it talks about algebraic. So this is what we are talking about. So it adds all the products, adds all the reactants. So you first add all the products, you add all the reactants, and then you find the difference. You find the difference. So we will look at this example in the class tomorrow, but please look through. I've solved it already. I want you to look through, and tomorrow's class is for us to just break it down if there is any need for clarifications. So standard heat of combustion. So in this case now, we are being more specific. So if the process is a combustion reaction, so we're looking at standard heat of combustion. And if you cast your mind back to when we looked at steam, and when we looked at the calorimetry last semester, so you see that it's a build-up, everything adds up. So you see that in those cases, it's all about combustion. You remember when we looked at steam last week, we talked about there's a combustion of fuel, and then there's a release of flue gases. That is combustion. Combustion of fuel, usually coal, and there is a release of flue gases. So combustion. So in that case, we specifically talk about heat of combustion. And how does heat combustion take place? There is a vigorous reaction between a substance and oxygen. In some cases, we just say air, but in specifically, we say oxygen. So when there's a vigorous reaction between oxygen, so for example, there's an explosion. So or you have a gas heater. I mean, you turn it on, a gas heater, a gas cooker, that is combustion taking place. So fuel is being burned. So we have that. So we've mentioned so take note of that, and evidently it is an exothermic reaction. So that is why we say it is negative. Heat is being released. So evidently, undoubtedly, it is exothermic. However, the heat itself is positive. The heating value is positive. Why? Temperature is increasing. Temperature is increasing. So that is evidently sure. So here's an example, another definition. So what I've also done is so that you could also, apart from I indicated last semester the textbooks that I've been using, and some of these textbooks are even available online. So while I've done that, here as well, you see I've also, there's an open text online. I've cited the website for you, for those who want to just have extra look, I want to look at many more examples and read more. So I've done that. And please also take note of just re-emphasis on what I've mentioned earlier on, the fact that it occurs when we're talking about anything standard. These are the standard conditions, 25 degrees C and 1 atmosphere. So for example, I give you values to say, these are the heats of formation for these different compounds. I show you at 25 degrees C, at 20 degrees C, and then you are asked to calculate standard heat of reaction, but you've been given heat of formation at different temperature for the different compounds. What do you look for? You look at the temperature. So you look at the conditions, you look at the pressure, and then you pick the right one. So please take note of that. So as I've said, more definitions. We've seen calorific, we've seen that before, calorific value. So I'm not going to, we've seen this before in, that will be chapter 9, I think. So you can, those are just definitions. So temperature dependence of standard heats. So remember, we've said, so it's all about change in temperature. So change in temperature and change in enthalpy. So we can say, we are seeing from here, change in temperature, we are saying change in enthalpy is dependent on temperature. So that's what we are seeing here. So change in enthalpy is dependent on temperature. So we are saying that we cannot have, a process cannot take place without temperature. So we've seen that over and over again. So the heat capacity of the substance, we've seen that. So these are some of the equations we'll be working with tomorrow, which I've worked on already in the calculations that I provided to you on Blackboard. So these are the things we'll be looking at. So we have those values, we'll define them, and then we work them out. Typically, these things might not make sense until we start doing calculations. So I want you to go back to the calculations that I've already provided and look through them. I mentioned this earlier on as well. So when a fuel is burned in air or oxygen under adiabatic conditions, the temperature attained by the system is known as the adiabatic flame temperature. Any takers? Okay, I think I've written it out already. A reaction, I was going to ask if anyone remembers what an adiabatic reaction is, but I see I've written it out in the slide, so it's given already. So, so when there's no heat interaction between the reaction mixture and the surroundings. So no heat interaction, but there is heat within the system. So take note, so there is no heat interaction, but there is heat within the system. So, so for example, if you remember for the way bomb calorimetry works and the other, the bomb calorimetry, so there's no exchange with the environment, but within the system, we said that is why it is called bomb calorimetry, because there is an explosion taking place, which is exothermic, but the process itself is adiabatic because it's shielded from the surrounding, from exchanging or releasing energy, temperature, and we've talked about. So these are, so we can just, so for another thing you might want to do is, in some instances, maybe you want to have a list of equations. So to say, for example, chapter 12, these are the equations needed. You write them out. Chapter 13, these are the equations needed, so that whenever you look at the question, then you'll be able to make sense of them. So we'll be looking at those questions. And then I've also cited, I found, apart from the textbooks that I used, I found this open textbook very, very useful. It's got so many examples. So please go through these examples, additional, so go through